Good evening to everybody, my name is Gonzalo Canano, and I'm going to present solving aeronautical problems as my key activity of physics. So, we're going to study the behavior of the helicopter in multiple scenarios and problems that they have been presenting since they were first built. This machine has presented some issues like the one we're going to talk about today, and we're going to try to solve it. So, unlike the plane, the helicopter flies at lower altitudes, which it means they have around 2 seconds to react as a pilot with the co-pilot if they want to avoid a fatal crash. So, because of the flight mechanics, the plane has around 20 to 30 times the height or the altitude they are flying to land a perfect arrival to the ground. Meanwhile, the helicopter, it only has 2 to 2.5 times the altitude they are presented. So, what happens when the engine dies while flying? Well, the direction of the pilot or pilots must be extremely fast if they don't want to finish in tragedy. So, the most effective maneuver we're going to talk about is the outer rotation helicopter. Well, this basically means that its transmission disconnects from the engine, so the air going down makes them kind of plane and land in a better way rather than the free fall. So, but most specifically, we're going to talk about the tail rotor. This specific part is responsible for compensating the torque the main rotor is producing, which is produced by the engine, but it's multiplied by the transmission. What does it mean to lose it while flying? Well, the issue you're facing is a tail rotor failure. Losing the tail rotor in the helicopter means that we're missing that part that is responsible for compensating the torque. What is going to happen? So we're looking at this as the helicopter, as a fuselage. This is the main rotor, and here it is the tail rotor. So if we miss this part, the torque and the thing is going to make it turn in the opposite direction that the airfoil blades are rotating. Well, our testing and experimentation was what, why, and when, and how can we solve this? So we prepared the planning, reporting step by step, and following a protocol, and a strict, clear, and organized protocol. We carry out a planning report step by step without losing details about the possible improvements that they could be made, and make some different tests so we could get the better result as possible. So we had to consider these variables. The independent variables, which is the weight of the aircraft, the altitude. The dependent, which is power. The control, which is climatological conditions and general characteristics of the aircraft and the parameters. The normative flight of the helicopters. So, in our specific case, we're going to talk about the Bell UH-1V1, so commonly known as the Huey. We have around, depending on the model and depending on the year of production, around 8,000 horsepower, and that translates to around 24,000 pound-feet of torque. And so our solution presented was consisted of adding a tail boom, which is a little blades or streets going from the beginning of the tail to the end of the tail, which is close to the tail rotor. So, in other words, they create a difference in speed between the one side and another. That creates a pressure difference that produces an usable torque thrust and torque that compensates the missing tail of the rotor. The applications, but we're more interested in designing the same for the Bell. And this modification was adapted adapted, so it's still being tested, and programs simulate the real-life situations with the specific environmental conditions that we are facing while flying. The results that we had is that the tool T-bone straights are the most cost-effective, multifunctional, value-added modifications ever developed since the single-rotor helicopters have been enclosed. They work by organizing and controlling the rotor wash, reducing undesired sideways lift on the left side of the tailbone by reducing the turbulence under the tailbone. We save up to 150 pounds of additional outground of hovered performance and up to 38% of reduction in the tailbone rotor. So what we can conclude: safer rides, longer last engines, better fuel economy, better control in multiple conditions, more power available in the main rotor, less maintenance, reduction of operation costs, and less structural fatigue on the fuselage. These were the references used in the